So first of all, here's the Navier-Stokes equation that most of us know and have come to love. And this equation represents the conservation of momentum in a fluid. And if you look at the little video that I posted on Blackboard, it explains a more kind of a physical argument of how this equation is derived. A physical argument being the equation of conservation of momentum for a first of all for a control volume, and then this taken to the limit of an infinitesimal small volume of fluid. So if you're not familiar with that, go and have a look at the video. So on the left-hand side of that equation, we have the acceleration terms. Okay, this is the acceleration for a small infinitesimal element of fluid. This term is what we call the unsteady term. It indicates the change of velocity with respect to time. And this term is what we call the convective acceleration. So just to remind you in case this is not fresh in your memory, or you haven't seen it in a while, or you haven't seen it altogether. This is the unsteady term. This is what we call the convective acceleration. This part? Yeah. Yeah. And the convective acceleration really represents, so the velocity is a vector field, right? And as a field, it has a different value in space. So the acceleration has these two components, because one component represents how the velocity of an element of fluid changes with respect to time, for whatever reason, forces and everything. And the other one represents how the velocity changes because a particle of fluid moves from one place to another place. That's why we call it convective. As a particle of fluid, a small little drop of fluid moves from one place to another place, it has the effect of moving within this vector field, and therefore its velocity changes. That's this contribution over here. On the right-hand side, we have the gradient of pressure. And again, if you want to see how this is derived for the particular case of the Navier-Stokes equation, it's in the video that I posted on Blackboard. It's the gradient of pressure, the thermodynamic pressure, and here we have a term which depends on the viscosity of the fluid and represents the viscous diffusion in the fluid. So this is a particular expression of the conservation of momentum. And the expression that we're talking about is one in which we have made a certain assumption about the behavior of the fluid with respect to the stresses. And that assumption that we've made here is that the fluid is a Newtonian fluid. Okay? What does it mean to be a Newtonian fluid? Anybody have a kind of a volunteer, an idea, just the basic concept? Can you, if you recall, how to... Stress and strain rate are linearly related. Exactly. That's the definition of a Newtonian fluid. Basic definition. So things that are not Newtonian, for example, are well, really the blood is not Newtonian. Okay, it's really not. Sometimes you can make the Newtonian assumption if you're studying things related to the blood, because for whatever reason the velocity, the accelerations are not within a regime that the non-linearities are very visible. But really, if you were going to look at the relationship between the stress and the strain, which is the derivatives of the velocity, it would, for the case of the blood, would be nonlinear. Things like yogurt, mayonnaise, all that stuff, all that gooey stuff, all the stuff that when you actually imagine what happens to yogurt. You see a cup of yogurt, and and it's kind of like solid; it doesn't move, right? But if you put your spoon in it and you spin it quickly, it suddenly becomes really liquidy, doesn't it? That's the property of a shear thinning fluid, which is non-Newtonian. It behaves non-linearly. What else? Well, of course, the famous one is the mixture of cornstarch and water. You've seen those videos in YouTube of people walking on water, which is really, just people jumping on a mixture of cornstarch and water. When you hit the cornstarch and water, you're applying a very sudden acceleration. It behaves suddenly very, very viscous. But if you move it very slowly, the viscosity is quite slow, and you can mix it like it was a liquid. That's very funny behavior. So in the Navier-Stokes equation, we have made the assumption of Newtonian fluids. We've also made the assumption that the density is a constant. That is, we're neglecting compressibility. So here in this equation, there are no compressibility effects. So we've made those assumptions. I think those are all. But notice that one of the very important characteristics of this equation is that in this term, we have the velocity multiplying derivatives of the velocity. Okay? So we have a nonlinearity here. This is a nonlinear term. Okay? This nonlinear term, well, notice it's a second order. We have second order here terms, second order derivatives. So this is a second order nonlinear partial differential equation. The nonlinearity is the source of most of the difficulties and what makes this equation very interesting. Now, if you make the assumption in addition that the flow was ideal, inviscid, so the viscosity is equal to 0, then we get the Euler equations. The Euler equations are, well, very similar to this, but the only difference is that we don't have this term here. This is 0, so I don't have that term. Let me just not write it. Okay? And this one are the Euler equations. Now, the Euler equations, of course, is more simple. We don't have viscosity, but notice that it's still nonlinear. Okay, so it still has these properties of the Navier-Stokes equations that are going to make them a little bit difficult to analyze and to compute. So in the inviscid approximation, we still have this nonlinearity. So now a question is, what is CFD? What is CFD? CFD is, well, we're going to analyze fluid systems and by means of computer simulation to get a solution. What is a solution? What constitutes a solution of this system? Well, a solution is, well, we want to know, first of all, the velocity. A solution will have to give us the full velocity field. And notice that this is a vector, so in every single point on space, we would like to know 3 values, the 3 components of velocity, and the associated pressure field. The pressure being a scalar field. Now, this is just for the Navier-Stokes equation, but in more complex situations, and then the Navier-Stokes equations would have to be coupled with perhaps heat transfer equations, chemistry, reactions. Inside an engine, for example, you'll have chemical reactions. A lot more complicated things will appear. You can couple the Navier-Stokes equations with those phenomena. We're not going to have time to discuss those very much, but you can see that it can get quite complicated. So now the next question. So this is the basic scenario that we're going to start with. So the basic, the next question is, why do we need CFD? Why would you actually need to simulate these equations computationally? So the first reason is that there are there are some, but the very, very few known analytical solutions to this equation. Very few. like 1, 2, 3, 4, few. And the only way to find these analytical solutions is there are very particular situations of symmetry, for example, that make this term go to 0. Say, because you have a particular 2D thing that is exactly everything moves like that, the velocity field is, and so in that situation where, for example, the velocity field is, unidirectional and it has only one component, and the thing is in 2D, so it's flat, and this term goes to 0, you have non-linearity, it disappears, and then you can solve the equation. Very, very few cases for that. Like flow inside a pipe, that's it, laminar flow inside a pipe, and flow between 2 plates or something like that, or flow between 2 concentric circles. That's all. Very, very few. So in reality, for applications, we are left with only 2 options. Real applications in engineering, we're left with only 2 options. Experimental or computational. Those are the only 2 options, right? Okay, so what? Well, we could just say we're going to do experiments and do experiments and then be done with that, right? So it's easier if we don't have to learn to program computers. But what if, what if you want to do study a system like this? That would be kind of difficult to do through experimentation, right? What if you want to study, for example, the effect of breathing particles of different sizes in the human airway? It could be a little bit complicated to do experiments in vivo. It would be, perhaps, you couldn't do experiments with humans. And so clearly we cannot do easy experiments. Even if we could do experiments, how could we even see inside, right? I mean, we could make somebody breathe something. How are we going to see what's happening? So many times we are going to want to do simulations because experiments are either too dangerous or unfeasible. And even we might do simulations because the experiments are feasible, but we cannot see what's happening. We want to visualize the solution. We want to actually be able to have information about the solution in a system which is, inside something. It's not transparent. We have to do the simulations for that. So it's kind of like CFD enables you to virtually go inside, see what's happening. Other reasons. So very quickly to test many scenarios of what if, and I can tell you, for example, this story of the fact that CFD was used successfully to study the flow around the swimmer in the stretch position, and this allowed to identify the areas of high drag, which was used to design the Speedo suit. Right? So to get to this point, what they did is they were able to make a model and then ask questions, what if, and change the model, change various parameters, and repeatedly change parameters to explore a parameter space and come up with some optimal solution to something in terms of design. It's an excellent reason to do CFD. And, what's this other one? Situations of mechanical design, for example, where you can optimize a solution for the particular purpose without actually building a prototype and making experiments over and over again. And of course, there's another one that maybe you haven't thought about, but it's more revenue making, which is entertainment. So, their fluid simulation is used in entertainment as an unexpected success of CFD, in fact, and this is the case of a simulation by Professor Ron Fetke from Stanford University. And indeed, this is a professor of a university who has been awarded an Academy Award in February 2008 for his work in movies through fluid simulation. And there's a whole new wave of using CFD, which is in entertainment, because doing simulation just based on art sometimes produces things that that they're not physical. As a moviegoer, you see this, it doesn't look real, and so they want to use physics to produce these images so they will be actually realistic, and then the moviegoer will be satisfied that what he's seeing over there looks real. Isn't that cool? So that's another application. And one final application that I wanted to share you, which is really cool, I think, as well. So consider this one. With funding from the Office of Naval Research, some researchers in Penn State studied the fundamental fluid mechanics of the odorant transport in the canine nose. So This, of course, the objective is to be able to design an artificial nose. So the interesting thing is that when a dog sniffs something, the molecules, the odorant molecules, which exist in very, very trace numbers, okay, very few per million or whatever, go through a very complex labyrinth that is illustrated here, a very, very complex labyrinth of passageways, which maximizes the surface area and the possibilities of the molecules to being, meeting one of those cells that receptor cells that are able to identify them. And so it's just nature here designed a fantastic fluid mechanical device that allows the molecules to be delivered to the receptors, right? And so, because that's when smelling occurs, when one particular molecule meets one of these receptors and signals the brain to say, this is such and such material. So to be able to see this process, what the researchers did was produce a complete model using MRI and MRI scans, a high-resolution MRI of an actual dog, of their passageway. Then they made a 3D model of the whole labyrinth of passageways in the canine nose, and they were able to, through simulations, show that there was a single passageway, which has the name dorsal meatus, which was responsible for the great capacity of the dog to smell. Of course, one of the objectives is to be able to design something that is, suppose that dogs are still used. It's very expensive to use dogs for, say, drug control in the borders. It's very expensive to train the dogs. The dogs are moody. They sometimes get sick. They train them for a year, then they can only work for a couple of years more, and then they get old or something. It's very, very difficult and expensive to use dogs for explosives, for all of these things. So they want to have some device that they could just use instead. So it's a huge project, millions of dollars. The team continues to work on this. It's DARPA funded now, multi-institutional project called the Real Nose. So that's just to give you a bit of an idea of the type of things that one can do, CFD. That's a very cool, I think, example. So today I just want to give you an overview about the basic ingredients of CFD and get you started with this assignment that we're going to have. The first assignment, the first practical module of this course, which is going to be something that we call in our group the 12 steps to simulating the Navier-Stokes equations, and I'll tell you more about that in a moment. So what are the basic ingredients? Fruits and vegetables? No. The starting point of any numerical method is, of course, a mathematical model. I talked to you about the Navier-Stokes equations a moment ago. Basically, what we need always is going to be not necessarily the Navier-Stokes equations. They're going to be another set of equations, but it's going to be a set of partial differential equations, usually, right? Or integral equations, integral differential equations it could be. And of course, there are associated boundary conditions. Never to forget our boundary conditions or initial conditions. And this model will apply to our target application. So always there will be, it's important to know that there's always an unavoidable level of empirism in the models. It's important to know that because any model assumptions can result in errors. Now, it's been known to happen, this is not unusual to happen, that discrepancies between a CFD solution and an experiment, which normally gets blamed on the CFD, okay, ends up being due to the fact that the mathematical model was not an appropriate description of the physical problem to start with, okay? So that's why it's very, very important to understand the physical model and understand what are its limitations. So physical models, complex, we talk about the Navier-Stokes equations, which are already complicated because they're nonlinear. And this nonlinearity is a source of turbulence, shock waves, vorticity interactions, all those sorts of phenomena, very complicated phenomena. Now, you can add combustion and multi-phase situations, bubble dynamics, evaporation, condensation, of course, of great importance in atmospheric fluid mechanics and meteorology, and then you can get really, really messy. So you always are going to assume certain simplifications, and that you need to understand. You need to understand what the model simplifications are, so then any discrepancies with the experiment don't get blamed on the CFD solution. So this is important, that the mathematical model is always associated with a particular target application. For example, what are the possibilities? Well, we could have incompressible, let me just change here colors. We could have an application of incompressible flow, inviscid, or maybe it applies with inviscid or ideal. Maybe it's turbulent. Well, maybe we're happy to do a 2D or 3D simulation, and so on. All of these simplifications are possible, and you need to understand really if that implication is that simplification is appropriate. You must always bear in mind the fact that the model already includes simplifications, and the solution method now is going to be designed for this mathematical model. So whatever we have assumed now is carried on forward. Okay? So what is the discretization? So after selecting the mathematical model, we need to select a means of discretization. So the means of discretization refers to a method for approximating the PDEs, or integral differential equations, by a system of algebraic equations. And those we know how to solve, right? We know we can apply a linear solver and we can solve those. So basically, we want to suppose that this L, curvy L, represents a differential operator which is applied to a function. You use a function of space, so let me write it this way. So L is going to be applied to a function u of x, where x can be 3dx, right? So this is a differential operator. So we have L of u of x is equal to f, a function of x again. So this is, suppose, represents a partial differential equation. And we want to convert this to ax equals b, which we can solve. That's the discretization means. A means of being able to go from one to the other. The most important methods of discretization are finite difference. We will start with that. FD. For CFD, the most important methods. Finite volume. We will see some of that too. Finite elements. Finite elements also is used quite a lot in fluids, in material science, in solids, and we're not going to discuss the finite element method in this course. There's a full graduate course of finite elements here, and we just can't cover everything. So I'm going to leave that one out. Spectral methods are other possibilities. As I said, I will talk a little bit about spectral methods, at least the basics you need to be familiar with. And there are other methods as well. Boundary element methods. There's a famous professor in Oxford called Trefethen, and he calls these the big three. And what else? Boundary element methods, I was saying. These are less often discussed, but equally important, I think, and quite useful. I will tell you a little bit about them so that you're familiar with what it means. Boundary element method, or BEM. Cellular automata, there are other things. Particle methods, and this is something we work with in my group. All of these are different discretization schemes, okay? Ways to transform an infinite dimensional operator equation into a finite dimensional one, a linear system, a set of algebraic equations from 1 to n, finite. So because we're going from an infinite dimensional world to a finite dimensional world, obviously there will be some loss of information. There's always some loss of information. Here, again, as in the mathematical model, you need to be aware of that. Okay? So discretization method, really, this is the major process of CFD, right? The major aspect of TFD is the discretization. And let me just, there are two major aspects of this. The geometry, you have to discretize the geometry, and you have to discretize the model itself. The geometry is regularly what we call, what we want to do is turn both the geometry of our problem and the numerical mathematical method into numbers. The computers only understand numbers, okay? And so what we do, that's what discretization means, turning that information into numbers. The traditional way to discretize the geometry is what is called a grid or a mesh, but there are others. For example, the case of the particle is not very common, the particles, but the most traditional one is this. And so it's very important to realize that the outcome of a CFD simulation is going to be very dependent in both of these things, the discretization of the geometry and the model, the method that is used, the accuracy of the method, and also the way that you discretizate, for example, how fine the grid is, how it conforms to any bodies or shapes or objects that there exist in the system. And the goal of the numerical simulation will be the grid is also an object which we use to provide the solution. The solution will be the numerical value of all of our unknown variables at the grid points. So the grid is also an object that gives us a vessel for the solution. Okay? In this part, basically, all we want is to convert, we want all the mathematical operators DDX and etc. to be transformed into arithmetic operations. On the grid values, on the grid points. Okay, so I want to change this continuum operators into arithmetic operators, finite operators. But this is not the end of the CFD. The ingredients of the CFD are a couple more. We need to add some other things to make this tasty, and these are the analysis phase. Well, we haven't even solved anything yet. We're just talking about discretizing here. And so these are the other two, analyze and actually solve. And so in analysis, and what do we mean by analysis? So really, all numerical methods must satisfy certain number of conditions to be acceptable, okay? We use the word numerical scheme. A numerical scheme is simply, I was saying that the model, the discretization of the model is converting all of your continuum mathematical operators, such as the partial derivative with respect to time, or etc., into arithmetic operations. That is done via the numerical scheme. Okay, and the numerical scheme, all numerical schemes, must satisfy a number of conditions to be accepted, such as consistency. We'll discuss these in detail. Consistency, stability, convergence. And in addition to this, we must analyze accuracy. So analysis is an important part of CFD as well. And then solution. Well, we finally have to solve the numerical scheme to obtain the grid point values of all the flow variables. And oftentimes this requires it can require two things. Basically, at this level of the solution step, this final step, you can have two situations. You can have unsteady situations, time-dependent or unsteady. And in this case, you're going to get ODEs. And you could have steady situations. And in this case, you're going to get just an algebraic system of equations. And so basically the two things that we need in this step are time integrators and linear solvers. These are the two final things that we need. So these are all the things that we need in CFD. We need to understand the model, understand the assumptions of the model, appropriate to our target application. Once we have the model, we need to choose a numerical scheme, a discretization method. The discretization method consists of, well, the geometrical part, how we're going to discretize the space, and the scheme itself, finite difference, finite element, finite volume, spherical methods. We need to be aware of the analysis, convergence, stability, and consistency of the numerical method. We need to know how to analyze the accuracy, how to measure the errors of a simulation. There are techniques for that, or you need to know how to verify and validate your methods, your numerical calculations. Then we want to solve, so we need to know how to do time integration, and we need to know how to do linear solvers. The only final thing that I'm not including here is the post-processing. That is also very important. So because once a solution is obtained from the computations, you need to be able to visualize that to actually understand the solution and apply the thought process required for whatever is your purpose, understanding a physical phenomenon or designing an engineering system or something. So I haven't included there, but let's add it because it is important. Post-processing, visualization. It is really a very important. Okay, so there's some example visualization, flows with pretty pictures. Okay, it's not just pretty pictures actually; they're very useful to communicate our point. Okay,